Okay, so on page 506 on table 1, it gives you some examples of what we had briefly talked about yesterday, and that was, of course, some of the elements on the periodic table. We wanted you to make some notations on your table, and for the most part, I would say on every periodic table that you look at, let's just keep things simple. I know there's over 100 elements, but just to keep things practical, out of these 100 elements, I would say probably pretty close to 70% of them either begin with the first letter or use two letters within the name of that element. Okay, so one of the things we want to mention is when you look at table 1, okay, obviously, we got aluminum, calcium, carbon, chlorine, gold, and hydrogen. And just even in that case there, 5 of the 6 actually start with those letters within the name, okay? Okay, then in the column next to that, okay, example we gave was iron has Fe, mercury has Hg, and potassium has K, and sodium has Na. So why are those abbreviations used instead of just the letters in the name? So what words are actually used then? Yeah, the Latin word for that element. Okay. So then, as we go over to page 507, okay, atomic components. Okay, an element is matter that's composed of one type of atom, which is the smallest piece of matter that still retains the properties of that element. We discussed some of this yesterday. For example, the element silver. Okay, when you're identifying silver, what is the atomic number? It's what identifies the element. And yesterday, whether we looked at your table or some of you looked at the one on the wall over there, the atomic number identifies the element and the number of protons. So, silver has an atomic number of what? 47. Okay? So, again, when we're referring to elements like, let's say, where's element 92? And that would be on the very bottom. Has the abbreviation of what single letter? Yeah, for uranium. Okay, so for example, element silver is composed only silver atoms, and the element hydrogen is composed only of hydrogen atoms. Okay, no one would argue with any of that. A little further down, protons and neutrons are found in a small positively charged center of an atom called the nucleus. Now, how much of this information then is a review? Some of it, all of it, none of it? You tell me. Most of it is? Okay, good, good, good. We will start talking about electrons today. Okay, so protons and neutrons are found in a small positively charged center of an atom called the nucleus. We just had mentioned that is surrounded by the cloud containing electrons. Protons, of course, have a positive charge. Neutrons do not have a charge. And it's the electrons that are floating around the nucleus that have the negative charge. Okay? Atoms of different elements differ in the number of protons they contain. Okay? So it is possible for some elements to have the same number of neutrons, and that would be referred to as isotopes. We'll get to that a little further. We're not going to spend so much time what we do want to look at is on page 509, the changing atomic model. Okay, so how do you identify something that you can't even see? Okay, well, that was probably a problem for many scientists in this case, as we can see in the 1800s. Okay, so the changing atomic model on page 509. You know you know now that all matter is composed of atoms, okay? But that is not always known. Around 400 BC, Democritus had proposed an idea that atoms make up all substances. Yes, that's true. However, another famous Greek philosopher, Aristotle, disputed Democritus' theory and proposed that matter was uniform throughout and was not composed of smaller particles, okay? Aristotle's incorrect theory was accepted for about 2,000 years. In the 1800s, John Dalton, an English scientist, okay, was able to offer proof that atoms exist. So, which is pretty astounding when you look at the 19th century. We're referring to, in this case, in the 1800s. Okay, Dalton's model of an atom, a solid sphere, was an early model of the atom. You can see. So what they're saying here is it was theorized that with what we see is the idea that all of these different atoms that you see on the periodic table, okay, were all just composed of these spheres. Okay, so what we're saying, what it's trying to say is that in each one of these spheres, just go ahead and pick any number on the table. Okay, so if we're looking at 34, that is selenium, I believe. So inside that nucleus, we know the protons are found. And when you say 34, again, that gives you the number of protons and identifies which element you're referring to. So you say 34, you find 34 on your table and say, okay, that is selenium. Okay, so what is the approximate atomic mass for selenium? It looks like it's 70, I know some of them are hard to read, 78.96. Okay, so we're just going to say about 79. So the atomic mass equals 79. Okay, and it was theorized there's a certain number of neutrons and then electrons as well. Now, one of the aspects that we had mentioned yesterday is that the charge is needed to add up to 0 if it's neutral. Okay, so protons, denoted here, designate which subatomic particle. The protons, of course, which has a charge of what? Each one proton has a charge of plus 1. So to add up to 0, okay, which one of these has a negative charge? The electrons do. So if these all have positive charges, these have the negative charges, how many would we have to add up to 0? You'd have 34. Okay? Okay? And in that case, when we're talking about atomic mass, it's what's found inside the nucleus, which we know now is correct. It's just the protons and neutrons. But it was theorized by Dalton that even the electrons were found inside, and that's why you see that sphere on page 509. Now, when you say negative 34, yes, that's correct, but we're just talking about a charge, not a value. Now, that'll make sense when we get further on into this curriculum. Okay? Again, it's a charge. It's not a value. Okay? So then what we want to, and don't worry, we'll come back to this. Okay? Then, as we see on page 511, okay, the electron cloud model. Okay? By 1926, scientists had developed the electron cloud model of the atom that is used today. An electron cloud is the area around the nucleus of an atom where its electrons are most likely to be found. Okay? Electron cloud is 100. We're not too worried about the size. Okay? But one of the aspects that may be important, okay, not at this level, but it's something that the author decides that's worth mentioning, is because an electron's mass is small and the electron is moving so quickly around the nucleus, it is impossible to describe its exact location in an atom. Okay, and when we get further down the road here, there's a pretty good video that illustrates what it is we're talking about when we're referring to this speed here. Okay, picture spokes on a moving bicycle wheel. They are moving so quickly that you can't pinpoint any single spoke. Okay? All you see is a blur that contains all of the spokes somewhere within it. Okay? So when we look at that, it's what we actually call Heisenberg's uncertainty principle. It's where you can actually know the speed of these electrons, but you don't know where it's at. Okay? Or if you try to pinpoint its location, you really don't know how fast it's going. Okay? That's why it's called an uncertainty principle. That's the last time you're going to hear that at this level. Okay. Now, when we look at page 513, okay, we see table 3 there. Okay? And we see on the far left column, it gives you the element. Then next to there, its symbol. Okay? Now, the atomic number, okay, just like what we said when you picked 34. Okay? That identifies that element because it gives you the number of protons. That's what the atomic number is. So, if we're talking about that statement we just made, what's true about boron? Its atomic number, what can you tell me about boron? It has 5 what? Protons. And if it's going to be neutral, which it can be or is, how many electrons is there then? There would be 5. So that adds up to 0 then. Okay? Now, one of the things that you may have learned or thought about during learning about this periodic table, that these two are always the same. No, that is not the case, and we can see that with boron because it says the number of neutrons is 6. Now, for some of these elements, yes, the protons and neutrons will be the same, but don't rely on that. The electrons and protons can probably be the same, but not the neutrons. Okay? So then the mass number for boron is 11, just like what you would see on your table. I mean, it probably says 10.81, but we round that up to 11 because you really can't have a partial neutron. So we want nice whole numbers. That's why we don't say 10.81. Like on this table, it has a mass number of 11. Okay? And then in the far last column, the average atomic mass says 10.81, and that would match up to what you have on your table. So, why is this important? Well, it's the number of protons plus the number of neutrons then equals the atomic mass. Okay? So, in this case, when we look at selenium's atomic mass, we said we're going to round that up to 79. Okay? So when we do that, we've got 79 over here because we said that's the atomic mass. That's what we're plugging in for that value. Now, we know the number of protons we said was 34. Okay? So 34 plus n then equals 79. So how many neutrons, or how would you find how many neutrons are located in selenium? How do you get this variable all by itself? You're going to subtract 34 from both sides then. Okay? So upon doing that then, what do we get? 45? Oops. Okay? 45. So then the number of neutrons then is 45. Okay. And again, how we got that was these two numbers will equal the atomic mass. And that's what we're illustrating here. Because if we were to do helium, okay, we look at helium. Atomic number of what? How do we identify the helium? Number of protons, which is what? Okay, so we got a 2. And then the atomic mass for helium is what? Approximately 4. So in this case, protons equals 2, electrons equals 2, and in this case, neutrons then also equals 2. So in certain cases, sometimes the number of protons and neutrons are the same, or they do equal one another. But in other cases, no, that isn't the case. So again, these electrons are not found inside this sphere like Aristotle had thought, and also Democritus as well. So eventually what that led up to then was what we refer to as the electron cloud. And that's going to be some time we're going to be spending here with today, tomorrow, and into next week, what that electron cloud structure is. And what that means is, if you do a little bit of foreshadowing into that, or looking ahead, because this principle is so important that we want to make sure we spend adequate time on there. So if you turn ahead to page 520, okay, if you would do that, please. Okay. So what you see, it's saying the floor. Now this is figure 10 on page 520. So what we see happening, the floor level is saying it's inside the nucleus. So we're going to keep these numbers small for right now. So inside helium, for instance, we know, what do we find inside the nucleus of helium? Which two subatomic particles did we just read about? Protons and neutrons, because the electrons are not found on the inside like was originally thought. Okay, so we know, just like what we figured here, protons equals 2, neutrons equals 2. So then orbiting around the outside in this electron cloud, just like what figure 10 is trying to illustrate, is these are rotating around the nucleus. And how many electrons would that be? Well, 2. For right now, we're just going to say there's one there, and there's one there. They use dots in that structure, but these E's here are just illustrating what we call electrons. Okay? Now, as we look at page 521, I like how they set this up on page 521. It's what we call an octet rule. Okay? Because when you look at a stop sign, even if you're visually impaired, you can tell that that's a stop sign. Not because maybe it's red and it's got the stop written on there, but because of its shape. Because we all know that a stop sign is an octagon. Of course, it has 8 sides. So, a column then is a vertical depiction on the table. So, in other words, we could say this is column 1, this is column 2, 3, and then all the way up to what you see. But notice on page 521, which group of elements is missing according to that, is that a table or figure 11? Notice it goes from element number 3, or lithium, to beryllium, and then it goes all the way over to boron. But what's missing between them two? Just like what you would see on this table. You see, this whole area is missing here. Okay? And there's a reason for that. Okay? Those are what we call transition metals or transition elements. Okay? So for instance, like tonight, when you ladies are playing basketball, or on Saturday when you both are in your double header, okay, if you're on defense, okay, the shot goes up, it doesn't go in, you grab the rebound, and then chances are, if it's a post player that grabs it, they're looking for the guard. Okay, they throw it to the guard, and down the floor they go. They're transitioning between defense to offense. So a transition means going from one to the other, one to the other. And that's what a lot of them transition metals do. The examples we did yesterday was iron was one, manganese is another. Okay, what did you write in box 25? What did we tell you to write in that box? +3, because it doesn't say that on your table, but on the table on the wall it does say +3. So what that means is a transition metal or transition element can have more than one charge. It's one or the other, one or the other, just like offense to defense, offense to defense. It's a transition. So that is why we skip them for what we consider as the octet rule. Okay. Anybody just totally lost? I've been sitting here for the better part of, 22 minutes and I have no idea what's going on. Left outside. Are we on the bus so far? Because if you nod your head yes, that means you're telling me that you understand. So left outside, left middle, right middle, right out, left outside, left middle, middle, right middle, right outside. Okay. So what that means is we want to start labeling parts of your table. So I would suggest you get your table out, okay, if you would please, okay. So this will make a little more sense for the students in the far left outside, because what does it say right there? It says group, but there's S block. So your first two columns, just like what we said here, this could be column 1, this could be column 2. Those first two columns are known as the S block. And I highly suggest that you write that on your table, the S block above the first two columns. This is column 1. This is column 2. This is the S block. These two columns right here. Hydrogen is in the S block. That is correct. Okay? So these first two columns, column 1 and column 2, are in the S block. Okay? Now, when you go over to column 3, that has boron, then carbon, then nitrogen, and oxygen, fluorine, and neon, okay? Or boron, carbon, nitrogen, oxygen, fluorine, and neon. That is called which block? It says right here. This is called your P block. These 6 columns is called your P block, okay? That is why, with what we see here on your table or figure on page 521, these two columns here is your S block. Then these all the way over here on the right side is called your P block. Okay? Yes. Is what included? Yes. Yes, it is. It doesn't say it on your table, but way up top here it says S block. Okay, this, even though this table over here is old, it's maybe a little more concise or precise. There's always going to be some exceptions to the rule, and we'll get to what that means in a few days. But maybe not today, maybe not tomorrow. But next week we'll get into that. Okay. Then, this middle column, there's 10 of them. Okay? Which block is that according to this? And what does it say right below it, right there? Transition elements. And what does it mean to be in transition? Going from one to the other, from one to the other. Because a lot of these elements have more than one charge. That's why they're called transition elements. And the majority of them are metals. So from scandium all the way over to zinc. Okay? For scandium all the way over to zinc, on your table there's a set of 10 columns. This is your D block right here. Okay? Nope. bottom is your F block. Well, parts of that, yes, but in general, all of this is your F block. Okay? Because for those of you over here, what does it say right there? The F block, down here. Okay.
So, all of them except the LE and LR.
So, where is the P block? Which side of the table? The right side. How many columns are in the P block? There are 6. Okay, where's the S block? On the left side, how many columns? 2. There's an exception, helium. Helium's part of the S block. Okay? So, in case you're wondering, well, if it is, how come it's not right next to helium? Well, that's why it's on that table. It's not attached. It's called a noble gas. It's because it's stable, and since it is a stable gas, it belongs with the rest of its family, the noble gases. Okay. Then, for instance, gold is in which block? The D block. Okay. And then finally, your bottom 2 on the table is known as your F block. Yes? Yes. 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 But again, it's over with the rest of its family because it's a noble gas. Zinc is part of the D block. Well, it is, but it only has 1 charge. But it still it has properties similar to that. That's why it's in the D block. Okay. And again, for when you're using that table, it's on the wall. It's a little more concise or precise than what we're using. We just want very general terms, except for what we went over yesterday. Okay. Now, what we want to do is if you have notebook paper, that's fine. And what we're about to write down, I would not put on the back of this, even though it's a blank sheet. The reason is when you use it, you're going to be doing something like this. Okay? We're going to write the slide rule down. We're not going to apply it yet, but we're going to put the slide rule. And I would leave plenty of room and make it plenty big so it's easier to read. Yes, you can use notebook paper, but if you have a blank sheet, that would be a lot more beneficial for you. Okay? So, this is what we call the slide rule. Okay? So again, make sure you leave plenty of room so it's easy to read. And if you're one that, if you have that sloppy of handwriting, maybe you can copy that or someone will make one for you. Because if you can't read it, it's not going to do you any good. Okay, so this is what I call the slide rule. 1, I need to write it that big. 1, S2. Okay? Then leave some space and don't put it way over on the right side of your paper because you're going to run out of room. Okay? Then beneath that, we want you to write 2, S2, 2, P6. And again, Make sure you leave space between here. Don't put them right on top of one another or else it's going to be hard to read. Yes? You can do it either way. But on lined paper, what I'm saying is this. If these are your lines on your paper, I don't know if you want to do it like that, because then it's going to be too small. You can, but it's just going to be hard to read. Okay? Then we keep on going. Okay. Okay. Let you catch up to that for a couple of moments. Is there a glare that you can't see or something? Okay. All right. One of the things to help yourself out and how to use this as a tool, okay, whether you are looking at that table on that wall, what does it say right here? Periods. Okay? Notice, what does it say right here on your table? Periods. So what we're starting to see here, these are your periods on the periodic table. They've got the numbers increase just like what we see here. Okay? Period 1 only has 2 elements in it. 1s2, the first energy level, only has 2, hydrogen and helium. The very first energy level, or S block, can only hold 2. One is hydrogen, helium is the other. Then, if you go down to the second period, okay, and you're in the S block, okay, what is the very first element in the second period of the S block? Lithium. If you picked up on it just like that, you are very well on your way to understanding this. If you're kind of looking at this saying, I have no idea what's going on, again, playing catch up on this is not very beneficial. Please come in, talk to myself or someone else so we can stay caught up on this. Okay? An old military term. We tracking? Tracking? Not tracking. You're not saying anything, so we're not tracking. We're tracking. All right. So then, where is the P block on this table? Way over on the right-hand side. How many columns are in the P block? That's why you see that 6 on there. Okay? So, remember when we talked about a stop sign? How many sides does this? It has 8. So what we see happening is when you start adding all of these together, 6 and 2 gives you 8. That's our math that we want to be concerned about, right? So what is being left out in the D and F block? Which 2 blocks? D and F. What do we see that's missing on here? The D and F. You suppose this is all a coincidence, or do you suppose there's some actual science behind this? There's some actual science behind this. You learn something every day. So how many periods are we going to go up to? I mean, just don't guess. Use it as a tool. We're going to go up to 7. Okay? So we keep going, 5s2, okay? And notice What does it mean to be a periodic function? In other words, we're in the month of January. We know that our periodic function knows that February comes next, then March, then April. That's a cycle that continues every year where it just repeats itself. Okay? So what do we see here? These repeat themselves as well. That's why it's called the periodic table, because it's a cycle that continues to repeat over and over again. Kind of like your favorite song. This is going to be your favorite song before you know it. Now, what's that look for? Either one of you. It's going to be your favorite song. Yeah, so that's why you put it on repeat so you can hear it over and over again, right? See, you're tracking. Yeah. So if these continue to repeat themselves, what's coming next? 5 what? Then what? Then now, don't fall into this trap. How many of these periods are how many of these periods are going to be in the F block? There's only 2. You are correct. How did you know that? Because there's only 2 on your table. There's only 2 over on that table. Right. So some of you are really tracking. Yes. It's just a concise way, because if you did that, if I'm interpreting your question correctly, if we did that, if you insert this F block where it really belongs, all of these, notice it says these 2 numbers from here to here, here to here. If you insert them, these are going to end up way over here. So it's just a more concise way of writing that. And how many of you have done factoring in your algebra class? Do you know what factoring is? Okay, so when you factor something, let's say you had 3x squared plus 9x minus 18. These 3 have something in common. What is it? They all go into 3. So if we factor that, we take a 3 out, okay? Then we've got x squared plus what? Didn't think you'd learn algebra in here, did you? What a coinkydink. Isn't this wonderful? That math and science can go together like that. See, I can't believe how... Well, it sounds to me like we're throwing tantrums more than we are books, but that's just my opinion. But oh, okay, fair enough. Okay. So, and again, when we look at this, you can always go back to your original state. When you distribute that, distribute a property of math, okay? In other words, what happens when we take 3 times x squared? Get 3x squared. 3 times 3x gives you 9x. So that's why this periodic table is written the way it is. It's kind of like factoring that F block out so you can actually see it on that whole table. Okay. So now we're going to keep on. We're just about done. 6s2. What do you suppose is next? Seven S2. That's it. We're just gonna. We could do 7D10, but no, we're not gonna go any further. Now you're gonna want to be able to write really straight. Okay. I think some of this was going all right, but some of it's sloping down. Now what you do, this is where the actual slide comes in. Okay. So it's kind of like when you're in elementary, when we see kids, they climb to the top of a slide, and down they go. Okay? Then, climb to the top of the next slide. Slide down. Just don't start putting random lines on here or else this isn't going to do you any good. Okay? Then 2x or 2p6 to 3s2. You go ahead, yes, please put these lines in. Okay? So that it looks like this. And that's what we want your slide rule to look like. Okay, we'll go over our last coinky-dink. We'll be done for today. Maybe you ever heard of a coinky-dink before? Yeah. Talking with one of the seniors about college and professional football. Oh, I don't watch it much anymore. So what does he do? He shows up with the team he supports. And I said, liar! Yeah, makes for a good story. The older you get in these curriculums, the better the classes get. For some of you sitting here, this is the biggest waste of time. You might think that, but it's an orderly approach to different types of problem-solving aspects you're going to have to do. Because some of you, I'm just going into farming. I'm just doing this. Well, I'm going into nursing. Well, maybe that's true. Or how many of you actually administer medicine to your livestock? Well, you actually give it a shot. Okay. So, do you grab your bottle, you stick your needle into the bottle, come on, and you start withdrawing. You just, that looks like that's enough. That's what I'll do. You got to read the bottle, because it might say, for instance, 5 cc's per 100 pounds. I don't know. I'm just making that up. But that could be a conversion. You're just not guessing. Okay? So if it's 5 cc's per 100 pounds, okay, and it's a 500-pound steer, you're going to give it, what, 25 cc's? How many of you knew that right off the bat? Over here, did you know that right off the bat? I don't know. But anyway, the last thing. Okay, on page 520. What does it say? It says step 1. It says level 1. Electrons can it hold? 2. We just shown that. Okay? The second floor or second energy level can hold how many electrons? Okay? I mean, it doesn't, and it shows it right here. Don't get hung up on these lines. This is an energy level. Okay? That's what them big numbers are showing you. Okay? Then look at where it says the step 3. How many can the third energy level hold? 18. 10, 6, and 2. That's where these numbers are coming from. This doesn't go, they don't show you the slide rule at this level, but it makes it a heck of a lot easier to learn this material. Okay? Then finally, well, where does that 32 come from? Well, what's 14 plus 10 plus 6 plus 2? 32. Okay? So that's where these numbers in your book are coming from. Okay, we'll pick up with this tomorrow.